introduce today's speaker, Vitalii Konarovskyi, with the talk on central limit theorem for modified massive Arratia flow. Please, Vitalii.
Hey, thank you so much for the possibility to give a talk and tell you about our recent result in collaboration with Andrei Anatolievich Drogovtsev and Max von Renesse. And today I want to tell you about some Gaussian fluctuations in the modified massive Arratia flow. And before I will formulate the result, I would like to very shortly recall about the classical Arratia flow, since actually the modified Arratia flow or the construction of the modified Arratia flow or idea of that flow appeared or was experienced because of exactly the classical Arratia flow, and also it is actively studied, and somehow my result is related with the known result for the Arratia flow, which also I will mention a little bit later. Therefore, the Arratia flow, it is a system of Brownian particles on the real line, which looks as follows. Particles start from every point of the real line or some interval, and then they move independently from each other as Brownian particles with diffusion rate 1 until the moment of their meeting, and after that they coalesce and move together. And the simulation of this particular system, you can see here, this direction is the time, and you see that every trajectory here, it looks like trajectory of Brownian motion, and after meeting the Brownian motions coalesce. This from one hand side, this model looks like very simple model because you have only Brownian particles and nothing else. But it turns out that this model has many nice, interesting properties. And also it appears as a scaling limit of different models. Some of that I mentioned here on this slide. Also, and because of exactly, I think this reason, so the properties of the Arratia flow is now more or less good understood. Also, my colleagues from the department actively studied the Arratia flow. Here I included only one work, but there are many other works of my colleagues who also investigated, for instance, the central limit theorem, the duality properties, flow properties, and so on and so forth. So the list of papers is really very long. Moreover, the Arratia flow admits different generalizations. For instance, one can consider the family of particles which started from not only at time zero from every point, but every time they appears particle, and or at every time we have particles which start from every point of the real line, and then in the future they move as a usual Arratia flow. It is called the Brownian web. One can consider non-Brownian particles which coalesce, stochastic kernels, and so on. And today I want to tell you about one special model which I started investigated or actually proposed when I was a PhD student in the department, and at that time our idea was to make or to build more physical model than the Arratia flow, and physical in the following sense. So if we interpret Brownian motion as a mathematical model for particles, say for molecules in some liquids, it is natural to assume that molecules have mass, and the fluctuation of molecules or that particles depends on the mass. And if additionally you assume that particles after meeting coalesce, they must satisfy the conservation law. And therefore the mass of two particles after coalescing has to be the sum of I'm sorry, the mass of new particle after coalescing, it has to be equal to the sum of two masses, and therefore the diffusion rate, it should be slower. And actually this, it was the first idea which led us to the model which now we call the modified massive Arratia flow. And formally, the model can be described as follows. We have I call that Brownian particles, but actually just remember that in these particles, the diffusion rate will be changed after coalescing. So therefore, we have particles with masses, and they also, as before, they move independently and coalesce after meeting. And additionally, as I said, they have mass which sums after the meeting, and diffusion rate is inversely proportional to the mass. And here you can see the simulation of that particle system, and you see that here the diffusion rate is slower than the diffusion rate, for instance, here or here, and so on. The main difference between the classical Arratia flow and modified massive Arratia flow is the following. In modified massive Arratia flow, the behavior of every particle depends on the behavior of the complete system. Because as you see here in the picture, it can happen that you have a particle, but another particle came, coalesce, and then it influence on the behavior of the fixed particle because it will change the diffusion rate. In the Arratia flow, we doesn't have this property because after coalescing, you still have a Brownian motion and nothing is changed. And exactly this also difference makes the modified massive Arratia flow really very complicated for the investigation. At the moment, we understand many properties of the modified massive Arratia flow. We can construct the model which starts from instance of every point of some interval, and then mass of every particle at start is equal to 0. That means the diffusion rate is equal to infinity, and after coalescing, the mass becomes positive, and then diffusion rate is finite. We can also build a particle system which starts from, say, from every integer points. We know the large deviation principle, and so on and so forth. But today I want to tell you about one specific property which also satisfies the modified massive Arratia flow. Actually, I want to study the Gaussian fluctuations which are in the modified massive Arratia flow, in the sense which I will explain in a few slides. Before I will formulate the main result, let me shortly recall you the mathematical description of the model. If we denote by x ut the position of particle at time t, and this u, it means that particles start from point u, then it satisfies the following property. So actually it has to be a continuous martingale. You have the monotonicity property because after meeting you have coalescing, therefore particles, also because of the continuity, they cannot change their positions. Also, the motion is independent up to meeting. So therefore, the quadratic variation, which actually tells you about the correlation between particles, is equal to 0 to their meeting, and the diffusion rate, you see, is inversely proportional to the mass, where m denotes the mass of the particle. Also, I would like to also say also about importance of that model, as later we understood that the modified massive Arratia flow, it has very important connection with a few mathematical objects. So actually, it is a non-trivial solution to the Dean-Kawasaki equation, and this equation is used in statistical mechanics, for instance, for description of density of a huge number of particles, and actually for the simulation of a huge number of particles. And it is known that the equation which was obtained by Gin and Kawasaki, it has only the trivial solutions, and then there is so we understood that there was like so we need to correct somehow the equation, and the modified massive Arratia flow is a solution of one of a corrected Gin-Kawasaki equation. Since Gin-Kawasaki equation also has the application in the optimal transportation and in the construction of some analog of Brownian motion on the space of probability measures, so this makes some connection of the modified massive Arratia flow also to the theory of optimal transportation. And also one additional property which I would like to mention here, that actually mu t, you should read this equality as a large deviation principle, and mu t satisfies the large deviation principle with the Wasserstein distance with two Wasserstein distance on the space of probability measure with the second moment. Today, I want to focus on a particular case or form of the particle system. I will assume that particles start only from integer points of the real line. And here is the following reason. So actually, you have a few of possibilities to construct the particle system or the modified massive Arratia flow. Either you assume that particles start, for instance, from every point of the real line, like in the case of the Arratia flow, but in that case, you have to fight with the problem that particles must start with infinite infinite diffusion rate, because mass at moment at start must be equal to 0, and mass of every particle after. So at positive time, it is a Lebesgue measure of all particles, or which started from some interval and coalesced into the particle. And this makes the model really very complicated. For instance, in that case, we do not know whether these 5 conditions which are on this slide uniquely determine the distribution. We know some properties, but it's really very complicated for the investigation. You can also assume that particles start with some positive masses, and actually it is a case which I consider here. And so for simplicity, we assume, as I said, that particles will start with integer points. Mass is equal to 1 at the first moment. And after that, they coalesce. So here the difficulty with that system is that actually you have infinitely many particles, and it can happen that when you fix some particle, probably particles from infinity can come and change the picture. So therefore, this case also is quite complicated, but it is much simpler than the case when particles start from every point of the interval. And for that, for this case, we can say something about the Gaussian fluctuations in the modified massive Arratia flow. So therefore, now I will assume that now we have countably many processes. Every process describes the behavior of particle. Xk describe the particle started from the point k. Also, this xk, as I said before, and also in that case, they must be a continuous square integrable martingale. They also are monotone. Quadratic variation is equal to 0. And the diffusion rate is inversely proportional to mass of the particle. And we proved many years ago that such a family of processes exist, and these 5 conditions uniquely determine the distribution of this family of processes. Today, I want to consider the occupation measure. No, actually, we can work with any functionals somehow related with so constructed using the modified massive Arratia flow. But I will focus on one of the case, and I'm sure that this result can be also extended to other cases. We consider the occupation measure, where the measure counts how many particles are in the set A at time t. So actually, NT counts how many particles are in the set A at time t. So here we should be careful. Distinct particles are in the set A. Also, let me denote by P the set of bounded measurable and one-periodic functions. And then let's define the integral of the function f with respect to this occupation measure. Oh, the result that I would like to discuss today is the following one. So actually, this process, it satisfies the central limit theorem with some quadratic variation, which is given by such a formula. Unfortunately, we don't have the precise formula for the quadratic variation, and it is given via the covariance between the integrals with respect to the occupation measure. But as later I will explain you, there are functions f, and there is time t such that the sigma is strictly larger than 0. So therefore, the statement is not empty statement. It is not the case that, for instance, all sigma are equal to 0, and then you just have the convergence to the constant 0. No, so we still have some Gaussian fluctuations related with these functionals, which are defined as the integrals. Actually, this result was experienced by a similar result for the classical Arratia flow obtained recently by Andrei Anatolievich Dorogovtsev and Katya Hlinina, where they considered the same occupation measure, but for the classical Arratia flow. And then they proved the same central limit theorem, where the quadratic variation of the limiting distribution is given by some concrete formula, which is defined via the two-point density for the Arratia flow. So actually here, two-point density, it means that you consider two particles and then a time t, and then you consider the joint density between the particles. Of course, it is not the product of densities of every particles, because you have coalescence between particles, but it is known that the precise formula for two-point Brownian motion, and you can compute the quadratic variation as that. Unfortunately, we cannot get here a result. We cannot get a formula similar to, for our case, to the formula which was obtained by Andrei Anatolievich and Katya. And then the reason is, as I already said before, that in the modified massive Arratia flow, the behavior of every particle depends on the whole particle system. But in the Arratia flow, actually, that the second moment related with the integral, you actually can define via the properties of two particles. And it was the reason why two-point density appears in the formula. These both results for the modified massive Arratia flow and classical Arratia flow was based on the, I would say, on the classical central limit theorem for stationary sequences. Namely, if you have a sequence denoted by CK, which is stationary and satisfies the strong mixing condition, it means that the mixing coefficient goes to 0, and the mixing coefficient is defined as follows. You just consider the deviation between the probability of product of two events minus the product of probability, where the first event is taken from the sigma algebra generated by all elements of the sequence 2 times 0, and another set or event is taken from the sigma algebra generated by xn plus 1, and so on. So by all n, xk started from for k larger or equal than n. So therefore, if you can control that the moments of the sequence, and you know that somehow the mixing coefficient is summable, then you have the convergence to the normal distribution, which is given by the precise form. So therefore, to obtain the central limit theorem for either for the modified massive Arratia flow or for the Arratia flow, you need to focus on the strong mixing condition, and you need to find a good control for the mixing coefficient alpha. For the Arratia flow, it is not complicated to do because, as I said, you have that if you consider, for instance, Arratia flow here and the Arratia flow there, and you know that they do not meet, so therefore, then actually you can control the mixing coefficient quite easily. But since you have, since for the modified massive Arratia flow particles, so change the diffusion rate, so the control of the mixing coefficient is much trickier as for the classical case. And so to explain the proof of the theorem, I would like to now focus on the mixing coefficient and get a good estimate of the mixing coefficient for the modified massive Arratia flow. So therefore, let's introduce for a fixed function f, which we integrate with respect to the occupation measure. We introduce the mixing coefficient, so like that, where we so this m, it is a sigma algebra which are generated by the integrals. So let me recall that this is the integral from k minus 1 to k of f dn.
Vitaly, may I ask you one question?
Yes.
So can you construct your flow with masses as a measurable function of independent linear processes?
Yes, it is exactly what we are going to do. So we will use one property of independent Brownian motion, which is important to be able to construct such a map. And and also I will tell about that. To be able to control the mixing coefficient, you need to somehow split the Arratia flow on two independent modified massive Arratia flow on two independent massive Arratia flows. And if you can do that, and if you can control this error after the splitting, then you can control the mixing condition. So actually, it is somehow straightforward idea, but you need to be quite careful to realize it. And actually, I would say that all technical work is around this idea. Okay. So therefore, when I write here I, it means that my sequence I consider from I and below, and if j and this j, it is from j and up. So therefore, we can prove the following proposition: for that there exists a constant C, and they exist beta depending only on f and t, such that we have the following estimate. So having this result, you see that since you can control the mixing coefficient but by e to the power square root of the difference, so then it immediately gives you the convergence of this series. So, and after you can control also the moments, then you immediately get the central limit here. So therefore here, that actually the main goal is to prove this proposition. And to be able to prove that proposition, we use the following observation, which was also used for the construction of the modified massive Arratia flow, started from all integer points. Namely, we can prove that having a family of independent Brownian motions, like on the picture, that started from points 1, 2, 3, and so on, with diffusion rates 1, they satisfy the following property. If you fix some time t, then infinitely often happens the following event. All trajectories below the level n is less or equal, so then some level between n and n plus 1, and the next Brownian motion is strictly larger than this level. So roughly speaking, infinitely often you have gaps of such a form, where, as I said, all paths below the line is less or equal. So all trajectories started from 1 to n are less or equal than some level, and the next trajectory is larger than that level. And this happens infinitely often. So therefore, having this property, you can build the modified massive Arratia flow as follows. First of all, you build a finite particle system just by coalescing or taking trajectories of independent Brownian motion and then somehow coalesce them. And let me show how we do that. So if we have, so this is time here, and then you will have one Brownian particle started from 0. And then you consider one particle started from 1, so it is here 0 and here 1. And then at the moment of their meeting, so what you do, you just cut the trajectory, oops, I'm sorry. You just cut this trajectory, you remove it. And this trajectory here, you just press by such a way to change its diffusion rate from 1 to 1 over 2. So actually you get something like that. You press. But you always cut the trajectory with largest index. Then you can add path here. So, and again, so if you have here the coalescence, what you do, you just cut the trajectory here. So you cut the trajectory started from, you cut off the trajectory started from -1, and you press the trajectory started from 0. So this, oops, I'm sorry, you press it more. And then you repeat this for other particles. For instance, here, if it happens that you have coalescence, so with that particle, you again cut off the trajectory for that particle, and you rescale the trajectory, this trajectory, which probably will meet somewhere, so here, and then you need to also change this trajectory again. So take the old trajectory of the Brownian motion starting from 0 and use it for the construction. But this way of the construction gives you the following. Look, if the Brownian motions satisfies that property here, Then after this, this transformation which we did for the trajectories, all trajectories of the modified massive Arratia flow, if you consider them from 0 and n, that n+1 trajectory, also will be below that line. But when you add here, consider here trajectories and also do the same transformation by cutting off the trajectory with largest index and pressing the trajectories with lower index, you also see that you will have a gap again between the particles of the modified massive Arratia flow. So the same picture is similar when you go in the negative direction. Also, if you can transform this picture, and then also you will have the same property, but in the negative direction, where you will have the gaps that these particles will not intersect the line, and that one particle below also will be below the given level. And so with this property of Brownian motion, you see that when a gap appears for a family of independent Brownian motion, then you have a gap for the modified massive Arratia flow. And adding new and new particles will not change the particles between two gaps. So for the negative and positive part. So therefore, it was like the main reason why we can construct this the modified massive Arratia flow. But now, as I answered the question of Andrei Yurievich, we want to split the modified massive Arratia flow on two independent modified massive Arratia flows. Therefore, we want to consider the modified massive Arratia flow which started from the points 0, 1, 2, only from the positive points, and also for the points which started from the negative points. So therefore, you can do the following, the same construction for the case when particles started only from the positive points. So here you have the trajectory also again 0, and here you have the coalescence and cutoff. Somehow probably that, somehow like that, and so on. And this family for n Brownian motions we denote by kn plus. And also you do the same for the negative. But now the particle started from the point -1, it is the first one, and then after the then it is that trajectory, somewhere that, I don't know, somewhere like that, and so on. And this we denote by xk and minus. So as I already said, taking into account this gap property of the independent Brownian motion, you see, or you can easily observe that the processes will converge, and also in the discrete topology of the space of continuous functions, almost surely to the process xk. And the same for modified massive Arratia flow started from positive points, and for modified massive Arratia flow started from negative. And now to be able to control the mixing coefficient, you need to be more careful in the control of the gaps which appears. So actually you want to have like more precise estimates when that a gap appear on some interval in the space. So for that we introduce two events. One event, it is the event that a gap appear in the level j plus 1. So actually when you go to that picture, then here it is exactly j plus 1 over 2. And for A minus, it is also gap appears for particles or for Brownian motions started from negative points. And also let's introduce the union of these sets, and these new events, they mean the following. for instance, b plus n, it means that there is a gap between the Brownian motions, so that appears between 0 and capital N. And the same for b minus, but between -1 and -n. Then we can prove the following proposition, namely that for every positive t, there exists a constant c such that this probability can be, or the probability of the complement can be estimated as e to some power, where that power depends on some functions, which depends on t, and these functions each behaves like 1 over t for t close that are close to 0. And then you have square root n. So, and actually it is a very good error, because later we will sum them together and the serial will converge and so on. So therefore, now having this proposition, having this estimate, we can use the following idea. So first of all, let me mention or note that if you consider two modified massive Arratia flows, one Arratia flow started from all integer points, and another Arratia flow started from only positive points, they are constructed using the same Brownian motions. So therefore, if you know that there is a gap between 0 and n, then all paths after that gap, they must coincide. So it directly follows from the construction from this property of the gap, or how we, and also from the fact how we construct of the modified massive Arratia flow. So therefore, now having this estimate and having that observation, we can do the following. So let me recall that this alpha is a mixing coefficient. That are sigma algebras generated by the corresponding sequences, and where at n it is a counting measure. Also, let's define the similar functional, but related with the modified massive Arratia flow started from positive points and started from negative points, where this is the corresponding occupation measures. And also, you see that in this, so since our function f, it is a periodic function, and the modified massive Arratia flow is shift invariant, because the martingale problem is shift invariant. So without any loss of generality, we can shift this alpha as we want. So actually alpha ej depends on alpha e minus j. I mean, it depends only on the distance between E and J. Therefore, for simplicity, we will assume that E is equal to minus J. So actually J is here, 0 is here, and E is here. And now we want to control for that I and J the mixing coefficient. And to do that, we take two measures, we take two events, A and B, from the cylindrical, from the sigma algebras generated by the corresponding sequences. And then let's first of all note that for every event, we can find a Borel measurable subsets such that this A can be given as pre-image of that Borel measurable subsets. And then we can control this probability as follows. We, first of all, we use that representation. And then let's add, so here to this intersection, let's add the event that there appear a gap between 0 and j and between -1 and -e. So the probability has a large, so this probability is large. So therefore, so we have here the intersection. We do that also for the product of probability, plus you will have the error. Actually, you can estimate by that, by the probability of the complement of the events that you added. And now, if you know that there are gaps, actually this modified massive Arratia flow, which started from all points, you can replace by two modified massive Arratia flow. One modified massive Arratia flow started from points 0, 1, 2, and so on. And another modified massive Arratia flow started from -1, -2, -3, and so on. Because on these events, they both coincide. So therefore, the functionals also will coincide. You do that here. And then after that, you can forget about these events here, but you will have the same error. You will need to change the constant here. And then you see that you will have the probability of the intersection minus the probability, but here is the intersection of two independent modified massive Arratia flow, because they were constructed using different independent Brownian, different families of independent Brownian motions. So therefore, you will see only that error which you get from the control of the complement of the probability that gaps appear. And actually, it is the main idea. So it is the main idea how you prove the central limit theorem, because you can control that. You can control the mixing coefficient. Also, it is not complicated to control the moments of the occupation measure. And here the reason is that actually we can control the particles which comes from the infinity. And this control guarantee that expectation of integrals to some power with respect to the occupation measure is finite. And now, since I have a few minutes, I would like also to explain why our statement is not empty. Unfortunately, we don't have the precise formula. I mean, if you give me a concrete function f and ask me what is sigma, I cannot tell you. I can give you only the formula, say that it is the sum of covariances, but I do not know whether the sigma is, for instance, positive, or maybe it is equal to 0. But we can prove the following statement. If we assume that the function f, which we integrate, is an odd function and one periodic, and also has three derivatives which are continuous and bounded, then we know that sigma squared divided by t converge to the first derivative of the function to the square. And if you choose the function f by such a way that this derivative is not 0, it will imply that there must be times t such that the sigma would be strictly positive, because otherwise, if it is 0 for every times, then this limit would be equal to 0, right? But it must converge to something like that. And to prove this, we use the following idea. We want to make, first of all, somehow picture symmetric. Therefore, instead of the integrals k minus 1k of f and t du, we just a little bit shift them on 1/2, like every interval. And we denote that these new functionals by a tilde. And then we can make the following observations. First of all, the expectation of a tilde is equal to 0. And the reason is when you flip your function, so then it is odd function. Actually, then everything what will be changed just minus. But when you flip the modified massive Arratia flow, nothing will be changed. So therefore, this immediately implies that the expectation must be equal to 0. And then when you consider this fluctuation field, the fluctuations, so this object, you will have actually that one. But using the fact that you integrate and then you sum these integrals, you have this one. So therefore, so this equality in particular implies that you can control the error between your old process, which convert to the Gaussian object, and your new process, just like 1 over n, and here you will have the integral from 0 to 1 over 2. Therefore, when you know that expectation is finite, you have immediately convergence to 0. And also using the mixing properties of the modified massive Arratia flow, you also, as before, you can show that this new object also converge to the random to the Gaussian random variable with some variance sigma square. But since you have this convergence to 0, it is not complicated to conclude that actually it is your old sigma t. So therefore, now our goal is to obtain the same result for this sigma t. And to be able to obtain it, we use the following trick. Actually, we want to make t smaller and smaller. So therefore, we consider the event that your particle which started from 0, so the event looks like that. You have the particle started from 0, you have particle started from 1, and particle from started to -1. Then you have these levels, and then you say, okay, let's consider the event that particle is here, that particle is here, and that particle is here. Well, here probably something happens, do not know. But considering that that set B, you can and recalling that this sigma t square, it is the variance, and then plus the sum of covariances. So you can first of all consider that expectation and can say something about that expectation. Namely, we can rewrite this expectation as follows. On this event, you know that you have only your occupation measure or integral with respect to the occupation measure from -1 over 2 and 1 over 2 contains only one particle, and it will be the Brownian motion. And on the complement, you will have something like that. The probability of this complement we can nicely control, and we can show that it's converged to 0 quite fast. But this part, we can write the Taylor expansion for the function f. Therefore, you will have that the second derivative of f squared, you will have f squared at 0. Oops, I'm sorry, here should be the product. It is a typo here. It is the product, which is equal to t. And using that, you work with the odd function, it is 0. When you compute the second derivative, you will see exactly what is written here. Therefore, okay, for that you can you have this expression, but to control the covariances that are equal to the expectation, you can use this mixing property for the modified massive Arratia flow, and that covariances you can estimate by e to some power. And now it is important to know how the function beta depends on t. And we know that this beta, it behaves like 1 over t. So therefore, when you write 1 over t and then you will sum the terms, they will go to 0. And it gives you that 1 over t sigma t square, it is actually, so that term, which is for that, that comes from that. And you will have, so that term which converges to 0. And it gives you the convergence to the second to square of the first derivative of the function f, which guarantees that that sigma t must be positive for some times t. So here is some literature. Results of this works of this presented work is already on arXiv. And here I just included a few papers which are related with the modified massive Arratia flow. In particular, in that paper, we prove the large deviation principle for the modified massive Arratia flow and the connection with the Dean-Kawasaki equation. This is the original paper where we make the construction of the modified massive Arratia flow from every points started from every points of some in the case when particles start from every point of some interval. And this is a paper where we discuss the existence of the modified massive Arratia flow started from integer points, exactly the model that I discussed today. It is everything. Thank you so much for your attention.
Okay, thank you very much for the talk. And maybe somebody have questions and comments, please.
I have one small question. So you used your the construction of massive Arratia flow starting from independent Brownian motions, and assume that you also started from integers, and that there are few rules. You have monotonicity when particles meet their coalesce, and assume that diffusion is just bounded. When they coalesce, diffusion coefficient is bounded, and particles move independent before coalescing. Is it true that for this flow you have the same mixing estimate?
Only the question about the boundness. You assume that the behavior of particles is defined by some stochastic differential equation?
They satisfy stochastic differential equation. Yes, with nice coefficient. In your case, it is constant coefficient, but assume that coefficients are not constant.
So here we use if shortly the answer should be the following: if you can keep the gap property for the independent Brownian motion, that you immediately have the mixing property.
Yes, I understand, but you used concrete and very nice function when you glue these particles together, and the fluctuations for after coalescing were smaller than fluctuations of Brownian motions. But assume that the diffusion coefficient is not a constant.
Yes, it is multiplicative noise here.
Yeah, then probably you'll have the same estimate. However,
intuitively, so
yes, intuitively.
taking into account like that the reason or type of behavior, so your behavior is not much different. It's just changed locally, and that should not influence like on this global, I would say, more global property. I believe that answer should be positive. But
I have an answer because even if you have not diffusions but martingales, there was Alexander Shamov in his paper devoted to the law of iterated logarithm for deviation in one-dimensional stochastic flows. We considered Slepian inequality for martingales. So what we need to give an estimation of the maxima for several independent, even more, we have it for dependent martingales. We can do this, so I think that everything will work.
Yeah, I believe that there will be gaps.
Yeah.
But Vitalii constructed this massive Arratia flow as a function of a given Brownian motions. If variance, if sigmas are not constant, then maybe there is no nice function.
Why do you need especially the Brownian motions? So you have already independent diffusions. Why not to use it? It is the same. Yeah.
I mean, when you can split, so here
when you split, the diffusion coefficient may be different.
Why not? You can just organize the splitting in purely algebraic way as Vitalii did. He considered this Q, one, second, third, and so on, and then make an agreement. Here we can do the same.
Andrei Anatolyevich, I think that here is the question a little bit different. In our case, we use that our coefficients depends on particles which already interacted with each other. So they do not see, if you didn't have an interaction with some particles, before time t, then the coefficients do not see that other particles. They start see that particles only after the interaction. But as I understand, Andrei Anatolievich probably means, or Andrei Yurievich probably means that your diffusions depends not only on the particles which started to interact, but other particles.
My question was that diffusion coefficient depend on a point. In your case, it depends only on number of particles. So when they coalesce, the diffusion coefficient is just 1 over mass.
Yes, yes.
But if the diffusion depends not only on mass, but also on position
of the particles that
of the particles.
Somehow already
that they coalesce, yes.
That they coalesce. In that case, it should be.
Andrei,
Exactly.
you want to include dependence on the position of the
yes,
particle.
position.
Am I right? Yeah? Then this one-dimensional case, why not to change variables? Yeah?
Yes, maybe. So this was my question. I think that the answer is yes, it is possible.
But you cannot change variables. You cannot change time, because when you change time once...
Not time. I just
time.
Change, no, I want to change phase like we did when we have non-degenerated diffusion. We just do some, we take some function from this diffusion and get a new diffusion process with the with variance equal to 1.
Like,
but then drift appears.
Yes, drift appears, but I think that drift
doesn't play so much
does not have any influence. Yeah.
Maybe.
We have absolute continuity and so on. So why not? Yeah.
So your result is much better. It can include many models with different interactions. For example, diffusion 1 if odd particles coalesce, or diffusion 2 if even number of particles coalesce, and so on and so forth. So am I right?
I would say that yes, because here the result is based only on the gaps between Brownian motions. Therefore, if you any model which can be constructed from Brownian motion with the preserving of gaps, then you could get the same mixing property, and not only for functionals of that form, but also other types of functionals that have to depend only on that some groups of particles, right? Not like for the occupation measure, but you can consider anything what you like. So then yes, I would say.
Thanks.
Okay, some other questions, please.
Sorry, maybe naive question. Can coalescent particles become independent again? Is this taken into account sometimes?
So in this case, not, because so let me explain. Just tell you a few words why this case is not taken into account, because the model actually we wanted to have a model of continuous martingales which keep their order. And if you know that two martingales keep order, they must coalesce, because the difference is a positive martingale, and after meeting at 0, positive martingale must stay there. But if you say that, okay, instead of that, let's consider the Brownian motions somehow which reflects from each other, or something like that. And if you can still build them using the trajectories of independent Brownian motion, that I'm sure that you can get a similar result. For instance, you can consider that Brownian motions reflect from each other.
Okay. Thank you very much.
It seems that you also can get
understand. Okay, thank you.
Other questions, please? I also have.
I have one question that I probably asked already. Vitalii, is it possible to consider this model that starts from all points of space and time?
It's yes, it's good question. I would say I thought about that about the
After your talk, I think it is not, but maybe
Yes, yes, I think not, definitely.
I think not.
Suppose, yes, suppose that in this picture, you have starting points inside.
No,
There
no,
are
no.
continuum starting
You
points,
need to
and
organize
you will
mass
get
differently, Andrei Anatolyevich. You need to organize. So here, so I thought about, of course, if you take that mass is equal only the Lebesgue measure of particles which coalesce by
Then
one
it is,
dimension.
yes.
It is impossible, but assume that you write like the mass of particle, it is two-dimensional measure in time and space. So the picture is the following. So for instance, here you have many particles, but this group of particles coalesce into that particle. And then the mass is defined by that area. Then for me, it's not clear. But if you count the measure like we did for this case that I discussed, then no, it is not possible.
Okay.
Thank you.
Also, I have a small comment related to the argument that we have examples, at least we have existence of the functions which has non-zero variance, limiting variance. I think that it will be interesting to check the behavior of this variance when t tends to infinity. Why? Because when t tends to infinity, our particles became to be slow and slow. So I think that we will approach like independent Brownian particles finally. Yeah, and
Yes,
I
it's a good
think
question, but
that
I think
in this we will have even positive covariance, yeah, between
yes, I think that you should have positive, like strictly positive, maybe for almost every function.
yeah.
But it's complicated. It is very difficult to answer that question because in this, when you make t smaller, you use the independence between particles.
Exactly. Yeah.
But when you make t large, you should use dependence between particles.
Yes.
For modified massive Arratia flow, we do not know how to work well with that.
But you already have some good estimations, yes? You remember this question which is unsolved up to date, yes? So, okay, good. Thank you again for interesting talk. And Georgi, do you know who will be the next speaker?
Yes, it will be Mykola Vovchansky.
Okay. So
Harris
for today, so for today we finish up. And thanks everybody. And bye up to the next week. Bye.
Thank you.
Thank you for a very interesting talk and very interesting discussion after the talk.
Thank you.
Bye.